Great. Well, thanks for having me. Um, I'm a scientist at Meta Fair in New York, and I've been working on, I usually describe my work as optimization and optimization sub-problems that come up across a lot of fields, robotics being a large one of them. And actually, in talking to a lot of people here, I realized that a lot of people already know what differentiable optimization is for robotics. So if you already know that, sorry for some of the more basic parts of this talk. But if you haven't heard of it, this is kind of, I would say, an introductory talk that kind of plants some of the seeds in the space that I've been thinking about over the past 5 or 6 years. And one disclaimer before I kind of jump into some more of the details. I'm not primarily a roboticist. I do work with roboticists, but I don't directly do the robotics. So don't expect any kind of drastically new robotics in this. But I do know the machine learning and kind of AI and optimization side, and I have a good sense of some of the optimization problems flying around. So, like I said, this talk is kind of my perspective on some of these and maybe some interesting kind of meta problems or kind of other ways of thinking about optimization and the robotics pipelines. Um, I also usually focus on continuous optimization, which means continuous control. But some concepts from this talk will transfer into discrete settings as well. So I realized to this audience, I don't need to introduce so many of these problems. Even the talk this morning or the intro slides this morning had this list of optimization problems that ended up being almost identical to the ones that I originally put on my slides. So I thought I would copy and paste this picture that I took just to show the similarities. I imagine I don't need to go through so many of these for this audience, but I would say there are a lot of these optimization subproblems which involve optimal control and motion and path planning, where maybe the one difference that I would say I want to present and think about it in this talk in contrast to like the way that it was written this morning is that I like to think of optimization as being contextual. Like it's not that we just solve one optimization problem in isolation and then forget about like all of the other like similar instances of it. So that's why I wrote it in somewhat of this non-standard way where there's some conditioning or context that I'm calling X, and this is the state of the world or the history or some other context that we have about the system. And this kind of informs the objective, like what we want to do in the world from the state, and also informs the constraints, like what's actually feasible to do given the state of the world. And then once we have that, then I like thinking about the optimization variable, at least in this context, as being over like what I'm calling the Y space. And I know it's a little unnatural, but I think you'll see soon why I think it makes sense to think about the contextual optimization in this way, because it lets us think about optimization as just being a function that maps from the context to, let's say, the minimum of some or the argument of some objective that's like optimizing over these conditional objective and constraints. So this makes optimization just a function in all of these settings. So for example, in optimal control, X here would be the current state of the system or some representation of it, and then Y is the control sequences. And so now this Y star object that I'm writing is like the policy that maps the state to the optimal action. And there are a lot of other settings where if these repeatedly solved optimization problems come up. And now from this perspective, of course, there are a lot of things that we don't know how to model in the world. So we're using AI and machine learning to kind of estimate them. This could include things like dynamics or costs and goals that are either latent, unknown, kind of conditional or specified by human language or some other representation. We could learn constraints or landmarks or other things as well. And from this perspective, if we're interacting with all of these other kind of optimization subproblems in robotics, it turns kind of the parameters of these modules get somewhat absorbed into the optimization process. And from this perspective, it also, in some ways, adds parameters to the output of the optimization process. And the two, I would say, areas that I work on is one, differentiable optimization, which means differentiating the solution to the optimization problem with respect to these parameters. And this is useful so that we can now end-to-end learn through the what happens when we actually optimize using the models that we've learned. Because otherwise, without this, there's some kind of disconnection or mismatch between what the models are actually being learned for and how they're actually being used in this end-to-end system that's actually solving the optimization problems after fitting the models. So that differentiates it. You can think about it as differentiating y star with respect to x or with respect to some other parameters of these modules. It's conceptually the same. And then the second thing, I'm not going to highlight so much in this talk, but I'm calling it amortized optimization. And it's just about, now that we have this family of optimization problems conditional on something, but it makes sense to predict the solutions to these pretty rapidly. So I wanted to connect back to something from one of the earlier, the first talks today on the SLAM and other kind of estimation problems. And there was actually a question from the session earlier that I thought was kind of make the differentiable optimization, or I thought it was a good I thought it was a good example for differentiable optimization. And it's in some of these estimation systems like SLAM and that have some perceptual front end that has maybe learned components that are extracting features in other parts, and some back end that's actually solving the SLAM or other alignment or estimation problem. And here there's a question of, oh, even if you can certify the this backend optimization process, it doesn't say anything about whatever errors your front end module could be making. And I would say that part of why I would say it's in general a very hard topic, and maybe something that differentiable optimization isn't the ultimate solution to. But I would say one way of improving the errors that the front end system is making is to somehow give it knowledge of these optimization problems that the back end is going to be solving. Like give the front end feature extractors knowledge of that they're going to actually be used for performing SLAM or something, with some metric or some way of measuring how well the SLAM system is performing. So I'd also just like to give a highlight to a recent paper by Connor and others here on the SDPR layers on making this possible in these kind of polynomial optimization settings. So they add these the derivatives to allow for this kind of end-to-end learning. And maybe I've been saying the same thing for 5 or 6 years now, but we can do this to every kind of optimization problem, and not just SLAM problems, but almost every optimization problem that has some learned component that's conditional on it, we can think about as being some building block in some larger system. And now I want to briefly shift gears to some other topic that I've been pretty interested in lately, and it's on this other side, like the amortization side, and somewhat related to Kahneman's modes of thought, like the fast and slow thinking, and robotics, which we'll get to. And the idea is that now that we know we're repeatedly solving these optimization problems, I would just like to argue that if we solve these problems from scratch, and formulating the optimization problem and solving it from scratch is somewhat like the slow thinking mode of Kahneman, while I would say fast thinking is amortization. It's kind of learning a fast module like a neural network to predict solutions. And this is really important and helpful because there are some settings where doing this, like learning to predict the solution to an optimization problem, can be 25,000 times faster than solving it from scratch. And there are a lot of there are a lot of examples, and before I get to those, I just want to also say amortization. It's about referring to the finance term and also kind of building on the use in amortized variational inference. And it's just about spreading out upfront costs over time. So there's some expensive cost of maybe training this amortization model, but then once you train it, you can get fast approximate solutions to your optimization problems. And I'll actually quickly go through some of these, but all of these are referenced in this book or tutorial that I wrote. So there's actually a lot of existing methods in reinforcement learning you can control, like the what I have here already. They're already doing this, and also, like I said, variational inference. I'll just go pretty quickly through this. MAMO and other kinds of math learning also does amortization, sparse coding, other convex optimization settings, optimal transport, and also recently I've been instead of working on robotics, I've been working on large language models, where it's also there are a lot of interesting optimization subproblems coming up, especially for attacking them, where amortization and maybe differentiable optimization also makes sense for some of the subproblems. There we have a new paper on this just posted to archive as well. And if you're interested in this direction, I'm not going to talk so much more about it here, but you can see my tutorial on amortized optimization if you're interested in that. So I'll maybe finish this part by saying maybe if you're solving 10 billion optimization problems, then maybe there's some shared structure between them, and you can kind of learn from that. I'm sure people that are solving 10 billion optimization problems are already thinking about this. So I have two main kind of parts of the talk. How am I doing on time? Is it 10 minutes left? We'll do, including questions. We'll do 4 minutes each. So I think a lot about control problems. I know there are other kinds of problems in robotics as well, but to me, the control and motion planning ones have been the ones I've thought the most about. And I guess I don't need my usual standard introduction to optimal control. I guess you all already have a good sense of it. It's about modeling part of the world and interacting with that model. I usually think about in continuous spaces. So in robotics, it could mean the model of the world comes from Newton-Euler equations of motions, and interacting with the world means sending torques to the actuators. And yeah, I'm sure you all have seen many examples of controllers. I'll skip over this. There are a lot of types of control problems. This mostly shared with what I had earlier. I'll briefly pause here on this is a discrete time continuous control, and it's just the perspective of how it's an implicit function of the initial state, costs, and dynamics. And the idea is that the optimal solving this control problem gives us some implicit function or policy of these. And learning can fit in as well. So if we can do dynamics learning, value learning, and cost learning as well. And separately on the amortization side, we can also do policy learning to amortize this problem. And the idea with differentiable control is that we can kind of tie in this end-to-end learning signal. So maybe even if we separately estimate the value, cost, or dynamics, we still don't have a sense of how well any of these estimations are going to perform in actually deploying it on the real system in a controller. So these controller derivatives kind of add that end-to-end learning signal back into, or add them to the model. There's been a lot of work on how to differentiate it because there are a lot of options and trade-offs. The references are here. I'll briefly say it either gets to unrolling or implicit differentiation. I'll skip through most of it. I have a lot of examples of starting with LQR control. How do you do it? What does it look like? And then going into the non-convex settings. and you can do it with you can differentiate through the cross-entropy methods, iterations, and also if you have convex optimization control problems, you can also just use our differentiable CVX pi extension. I had another kind of related project on metric learning with differentiable optimization as well, which is trying to kind of learn a metric in the prediction space for learning dynamics and in some other settings. This was a NERVS paper from last year that you can check out and ask me later. There have been a lot of variations and other extensions. I'll actually just skip past quite a bit of this. There's a lot of parallels with kind of the smart predict and optimize literature as well. I think yeah, maybe I put too many references throughout the last part of this portion. But that's a quick tour through differentiable optimal control. And I'll kind of end the talk on this this other class of optimization problems on nonlinear least squares problems. And the idea is that there are a lot of other kind of these like estimation or like post-graph optimization problems or like square root SAM and bundle adjustment that can be formulated as least squares optimization problems. And yeah, all of these look like this, where now it's roughly the same form as I wrote before, where now we have some optimization problem that's conditional on like the weights and costs of these optimization problems. And the one idea is that we can do the same trick with all of these. We can just say, oh, we also care about some end-to-end loss that we can define on the output of these modules and optimize for that. And we've developed this Theseus library, also published at NeurIPS a few years ago, on being able to do this in a pretty nice application agnostic way. And before our library here, there were a lot of really nice but somewhat scattered implementations of people also doing this, like grad slam and other kinds of differentiable factor graph optimization. And because the implementations were pretty specialized, they didn't have, for example, like batching or GPU support, and they weren't able to leverage sparsity and had limited backprop modes. But now we can re-implement almost all of these settings with Theseus and kind of have a better interface with the differentiable optimization component for these. We have examples in post-graph optimization, tactile state estimation, motion planning, homography estimation, and bundle adjustment for showing a lot of other settings where you might want to use differentiable optimization when you're estimating some module that's being further optimized with any of these. There's been a lot of works developing on and also developing other libraries for differentiable nonlinear least squares that I've listed here. We have quite a few of the standard kind of internal components that you would expect as well, like the standard second order solvers. We support Lie groups, and we have a differentiable Lie group operations, and we also have other cost functions and quite a few options for other parts of the backends, like exploiting sparsity and the linear solves and parallelization, different backward modes option. I'll skip through that. And I'll actually end with a shout out to Pipos, which seem to have done a really good job at making a faster implementation of almost everything I've been talking about. It seems like I haven't personally used it, but it seems like it's a really nice library. They have two main contributions. The first is that they compare to my differentiable MPC library and show that they're faster than it. And then they compare to Theseus and show that they're faster than that. So it may be worth checking out if you're working in the space, or if you just want some motivations for other settings and kind of other applications that people are thinking about with the differentiable optimization. So that's it for the talk. We've covered kind of a quick tour and like a quick motivation and tour through differentiable optimal control and MPC. And we got into some of the differentiable nonlinear least squares problems as well. And yeah, maybe next time I can talk more about these ideas of amortization in robotics. Thank you.
Any questions for Brandon? Yeah.
Hi. You said you want to talk about amortized optimization later, but you did put something. So I'll ask one question. So I'm kind of confused, like that how is amortized optimization connected to differential optimization? Because if you are just predicting the optimal solution based on neural network, that is doing something that differential optimization was trying to counter, that don't learn the solution space, learn some kind of representation which maps to solution space. So it seems like that we have come full circle now. That we started with differential optimization to solve a problem. Now we're saying we're coming back to the old way of doing stuff then.
It's a good point and a good question. I like thinking about it with this kind of picture where if you take a point of the parameterization or of x, like I said, they're kind of the same thing. The derivative kind of tells you how that how the optimal solution moves there, but that's only for a single point. And the amortization, it's about understanding the solution across the distribution of points. And so I like thinking about the differentiable part as adding a kind of, it's a way of parameterizing the system where you know that there are neural models that are estimating components that are solved with an optimization problem. But then when you start amortizing it, it gives you this fast learning component. So to me, the differentiable optimization, it's for slow learning and finding out the optimization problem that you want to solve. And then once you know that, or maybe in the process of knowing that, you solve them fast via amortization. So that's kind of how I think about those.
Okay, I think in the interest of time, maybe we'll do one more question quickly.
Thank you. You highlighted unrolling versus implicit function theorem a few times. I kept seeing them sort of on equal footing. I was under the impression it would always make sense to use implicit function theorem if you're optimizing or differentiating an optimizer. So is there ever a time you'd rather backprop through the unrolled iterations?
The unfortunate truth is that the implicit differentiation only works when we're at a fixed point, which works well for a lot of the convex stuff that I've done. So all of the convex stuff, it's usually easy to hit pretty guaranteed fixed points. In non-convex settings, it's hard to say about anything. Like if we're not at an exact solution or a fixed point, I would say unrolling or the truncated version makes more sense because it's able to be aware of the actual computational structure around the suboptimum point that that the optimizer finished on, rather than making some suboptimal approximation that the solution is optimal, like the implicit function theorem makes.
Okay, thank you, Brandon. Okay, so we're gonna move on to our next speakers. It's actually gonna be a joint talk between Rinka Antonova, who's transitioning to a role as an associate professor at the University of Cambridge, and Yang You, who is a postdoctoral fellow at Stanford. And they're gonna be talking about differentiable simulation, the challenges there, and some ways we can get around them.
Can you hear me well? It's just a sound check. Is the sound working?
Yeah, I can hear you.
Okay. Fantastic. All right, so I'll get started then. Thank you for the introduction. Yes, so I will be giving a joint talk with Yang You, and we will be talking about differentiable simulation, the challenges and opportunities for that. And I just wanted to double check that the slide transitions to the next slide. Yes, we can see that. All right, so first of all, I'll just give an overview of what is the promise of differentiable simulation. I'm sure, we've been talking about it a bit during the workshop, but to make it clear, our simulator can be represented by a function. Here we call it function f, that is differentiable. And then we can directly propagate the gradients from our loss or objective function through the simulator. And what can we do with this? So we can, for example, adjust directly the physics parameters or some geometry parameters of the simulation. And this is usually referred to as a real-to-sim problem. So we can take real observations and directly propagate the gradients from the loss that aligns them that aligns the simulation with reality. We can also update policy parameters, for example, by doing direct trajectory optimization so that we can optimize the policy or behaviors of the simulated objects such that we achieve a certain desired end state or reach a certain goal. Now, I'll mention a few examples of differentiable simulation frameworks. For example, Nimble demonstrated speed up over using finite differences for high degrees of freedom robots, and Tiny Differentiable Simulator allowed simulating a large number of robots at high frames per second. Simulators like Dojo offered more custom approach, so they offered gradients that are modeled in a smoother way, even for rigid objects, and still remained analytic gradients. Now, it seems like there is a wide variety of these simulators, and I just mentioned a few, that there are many more examples. But we don't see differentiable simulators yet as ubiquitous. We see more often in robot learning non-differentiable simulators. So what's the catch? So first of all, taming the gradients for rigid context is still quite challenging, and I will talk about it during the later part of the talk. Making new scenarios still requires significant effort. So it's not as plug and play as with many of the general purpose non-differentiable simulators. And the smooth gradients or this gradients for the smooth context that I mentioned, they are usually defined for certain types of interactions, and it's not trivial to extend the simulation to, let's say, a new model of the robot, or for the robot to touch in multiple places as opposed to some predefined locations. So basically, the issue is that general purpose black box simulators are often faster and more versatile than differentiable simulators. However, there's still a huge potential that we can see because the optimization is more direct with differentiable simulators. So I'll highlight this potential as well. And Yang will talk later about an approach that also makes use of that. Now, I have mentioned the shortcomings or the difficulties with modeling or computing gradients for rigid objects. But let's take a look also at the deformables. So there are some early simulators that introduced differentiability into existing simulators, like the ArcSim, for example, for thin deformables like cloth. There are also frameworks like the Tai Chi that have both mesh-based and particle-based versions of simulation and have been used widely. And there's a newer framework called Warp from NVIDIA that is also catching up and adding some new functionality. One of our earlier works used this differentiable version of ArcSim to work with deformables, and I will just briefly mention kind of what can be accomplished with simulators like that. So the work we've done, this was published at IROS a few years ago. It allowed to infer physical parameters of object, for example, mass and stiffness, by propagating the gradients through meshes in the differentiable simulator. And to connect this to the loss based on real point clouds, we used a differentiable point cloud sampling to propagate gradients from the loss that was based on the chamfer distance between the simulated and real point clouds. So this way we could achieve real to sim directly from real observations without any further labels. Now, the resulting method, we called it diffcloud, achieved real to sim alignment significantly faster than the gradient-free baselines that I'm showing here on the right part of the plot. And that was because the gradient-free baselines, not only did they need to collect the data, but also they needed to train larger neural networks, whereas here with the diffcloud, we could directly propagate the gradients and the optimization was direct. So this was promising, but even in this work where we have tested it on a few versions of thin deformables like cloth and paper towels and things like that, we were able to see how the real to sim works. Nonetheless, we observed that we needed sometimes to run random restarts in order to find good solutions. So you can't just pick an arbitrary starting point and then hope that the gradient descent would get you to the optimum always. So before scaling up, we decided to run a thorough analysis of optimization landscapes that are usually seen or that we usually expect to see during differentiable simulation in practice. And so the next part of our work came as kind of an effort to do that. So this appeared a year or so ago in Coral. So we've created differentiable simulation environments with various objects and interactions. And we did analysis of the optimization landscapes and some visualizations as well to understand what are the challenges. And then we proposed the method that combined the global optimization with semi-local optimization and then with gradient descent in order to overcome some of the difficulties that we saw in these landscapes. So first of all, we've constructed scenarios with rigid objects, some benchmark scenarios, some challenging scenarios to specifically identify what are the issues with gradients for rigid objects. We've also looked at particle-based simulation with fluids and mesh-based simulations with highly deformable objects. And we also incorporated a number of particle-based environments from Plasticine Lab that simulated plastic deformation. So the challenge, basically in overall work, first we challenged the assumption that differentiable simulators provide easy optimization landscapes if we consider sufficiently interesting scenarios. And our visualizations, in fact, did show that the loss landscapes had numerous local optima. And for example, here are a few visualizations from the fluid scenario, where you would think because it's an interaction with a fluid, there's maybe the landscape would be smooth, but that was not the case. Now, the case where we did observe smooth landscapes were more likely to be from Plasticine Lab environments with plastic deformation. However, here we also noted that gradient descent could get stuck on a plateau because there were multiple plateaus where gradients would make very, very slow progress. So that was another challenge. And after observing all of these issues, we decided to propose a hybrid approach that leveraged global optimization to specifically Bayesian optimization that explored the landscape globally, while also reducing uncertainty about which parts of the landscape to explore next. This uncertainty was modeled here using a Gaussian process, and it basically allowed to pinpoint unseen regions which could be promising for then going in and using semi-local and local optimization to find the actual local optimum there. So just briefly how this worked. At each global iteration, Bayesian optimization proposes the next vector of simulation or control parameters to try. And then we treat this as a starting point for what we call semi-local leaps. And to do this, we first sample a population of candidates, and then from the best candidates, we compute the starting point for the gradient descent. So this semi-local sampling is gradient-free, and then from the best candidate, we do a local gradient descent using the differentiable simulation. Now, this gradient descent part is what we call the leap, because on smooth landscapes or on smooth parts of the landscape, it can make very fast progress towards an optimum that kind of beats the gradient-free methods. And then when the gradient descent reaches the local optimum, we again sample candidates in a gradient-free way. And then the way that we do the sampling is using a Gaussian distribution whose mean and covariance are computed by covariance matrix adaptation equations. And covariance matrix adaptation is a widely used gradient-free method that technically is kind of semi-local. Now, from this, we again compute the start for the descent from the updated mean that is obtained from the best candidates, and then we run another gradient descent and so on. And then in the outer loop, we update the Gaussian process posterior so that it tells us about where to sample next overall globally on the landscape, and hence we can start a new leap by combining or by sequencing the next set of semi-local semi-local optimization and gradient-based optimization. So that's overall the gist of the algorithm. And we have tested it on the environments that we've looked at. First, the benchmark environments, of course, starting with cardpole, where everything is smooth. And even though we have some of the, we have a rigid object, but we don't really have context here. The goal here is just to reach. Here we have observed that gradient-based methods did really well. However, actually the combination, when we started to look at the updated version of this, where our start state is further away from the goal, we see that we actually do need, even in this case, even in the smooth case, we need a hybrid approach that we have proposed, which is highlighted there in the black bar. Now we've also looked at plastic deformation. And here on the left, you can see the performance of CMAS, which somewhat solves the task of wrapping the rope around this pole. However, with the hybrid optimization, we were able to achieve a better result at the end, where the two, the goal here is to bring the two of the ends of the rope together to wrap around this pole. And when looking at the loss, you can also see that this black bar, the method that we propose, also performs better than either gradient-based or gradient-free methods. We've also tried some extended versions of this where we start further away from where these anchors that are pushing on the rope are starting further away from the ends of the rope. And we also observe similarly that the CMAS now struggles a bit in a gradient-free manner, but the gradient-based methods are actually able to make better progress. There are also a few other tasks that we tried. This task here is of moving magenta round sphere on top of the cube. And here these anchors are kind of trying to grab gently onto this magenta ball without squishing it too much. And you can see that only certain methods succeed to do it. And with the more advanced version of this, where the anchors actually start further away and have to get into a good kind of configuration in order to even start moving the magenta ball, we can see a slightly less obvious solution of this, where the ball is more like pushed and thrown on top of the cube. Nonetheless, the task can be still solved with this hybrid method. Right, so we also did real-to-sim experiments with an actual real robot setup. Similarly here, we've considered thin deformables such as cloth first, where we tried to infer the parameters of the cloth. And here we're just using a robot arm in order to lift up the cloth, and then using the cameras in order to look at what happens with the cloth. So the cloth is our deformable object. And here you can see that over the course of 1 to 25 to 200 episodes, we're able to align this cloth. And even on the 25th episode, we already can see that its stiffness parameters are matching reasonably well. And here we're actually looking at the many stiffness parameters for different parts of the cloth. And similarly, we could identify the higher stiffness for example, for a paper towel here. And the loss landscapes, they sometimes, for some cases, look a bit smoother. For some of them, they look a bit rougher. So that kind of there's a difference in how well different methods perform on this. But with this combination of gradient-based and gradient-free methods, we were able to reliably get reasonably good performance for a range of different stiffness and the properties of the loss landscape. Similarly, for the liquid, a few examples of how we've optimized. Now here we're not doing real-to-sim, we're actually trying to design a trajectory for the ladle that picks up both of the cubes. And in simulation, you can see that we've successfully done this with the method that combines gradient-based and gradient-free approaches. And we've also deployed this, just to check, we've also deployed these trajectories on the real robot. And again, you can see that on the left, sometimes there are issues with picking up both of the sugar cubes. Here, there are foam cubes, but the dynamics ends up being similar. While on the right, we actually succeed in picking up the cubes most of the time. All right, so what are some of the challenges that we noted that were a bit difficult to handle? So of course, one side note that I can say is that I've shown nice visualizations. In reality, these are a little bit slow to generate, just as visually pleasing animations. In practice, we use some kind of something that is faster to render, but practically this is the same. The challenge with using with incorporating methods like Bayesian optimization and CMAS that use matrix decompositions ended up being inability to completely root out non-determinism. So basically, the slightly non-deterministic, slightly kind of different outcomes remain even if we try to kind of like use the same initial seed. And so that makes the reproducing exactly the results a little bit difficult. However, what we can do instead is we can look at a range of environments, which is why we created this benchmark, so that if a certain method performs really well on a whole range of environments with different types of contexts, different types of deformations, then we can say that, okay, maybe overall this method does well, even though there are small fluctuations when you rerun a particular experiment. And lastly, we have actually developed this way of looking specifically at what are the problems with rigid contexts. And we have visualized a few of the landscapes that showcase that even if you simplify your domain to just have a few rigid contexts, you can have very challenging landscapes that come out of this. And only to a certain extent you can really mitigate this by somehow incorporating smoothness into this. But this probably is a very good open research problem where the new simulators can adopt more of this and kind of smooth it out and make it a bit easier to optimize on these landscapes. Similar problems hold for interaction with rigid and deformable. Slightly smoother landscapes here, but still a lot of spikes and a lot of challenges. So to summarize this part of the talk, well, if you see a simulation, the differentiable simulation that has well-behaved dynamics, it's not necessarily safe to assume that you have a smooth landscape. So you might still need to deploy methods that combine the gradient-based and gradient-free approaches. We noted that particle-based simulators yield high-quality gradients and smooth landscapes, so they're a bit easier to really make progress on. They're more computationally intensive, but we really point this out as a nice future direction that could be amenable to good optimization. And lastly, I can say that combining global search with semi-local optimization and then using the gradients to make fast progress on smooth parts of the landscape, it really paid off. And this is one of the kind of general frameworks that can be used successfully. And with that, I'll transition to Yang, who can finish the talk with his part, because there is also a way that he can present to address the challenges that I pointed out with a slightly different set of methods. So Yang, maybe you can share your screen. And you, can you unmute yourself as well?
Yeah, can you hear me?
Yeah, and share the screen again. Yeah.
Okay, cool. Okay, so yeah, thanks, Rika. I'm Yang. I'm a postdoc from the United Scripts lab from Stanford University. I'm very glad to be here to share some of our recent works and findings on differentiable simulation. So we are going to begin with this question. Can we use a differentiable simulator to teach the robot to manipulate the doll? We all know that it's relatively easy for an adult to manipulate the doll, but it's quite a still challenging task for robots. And yes, we have differentiable simulators with physics. Probably we can use that to solve our task. We can backpropagate the physical parameters and to backpropagate the gradients through our actions to solve this task. However, as previously shown by Rika, long horizon differentiable gradient descent is very challenging, and the loss manifold is highly non-trivial. So we cannot really use it for a very complex deformable manipulation task. Of course, alternatively, we can collect data to directly supervise the training, but it is relatively hard to get enough data for deformables since they have a large number degree of freedom. So can we decompose a task into differentiable solvable subtasks and in a zero-shot manner? The answer is yes. If you ask nowadays large language model on how to make a donut, it can tell you, okay, here is the first step. You need to flatten the dough. And here is the second step. You need to make a hole. So inspired by these findings, we propose a hierarchical way to manipulate the dough. In the top level, we have large language model guided multi-tool planning module, taking the user input prompt and the context prompt, not shown here.
we ask GPT how to complete the task. And for each stage, given the tool to use and also a Python code to generate intermediate subgoal states. For example, here in the first state, GPT-4 will probably say, okay, I will flatten the doll using the rolling pin. The tool name is rolling pin, and it can also give you some Python code to generate that. And in the second stage, it kind of identifies, okay, we need to create a hole, and it can give you the code to generate the particle state. And we did ask GPT to generate state point cloud instead of the raw robot actions, because we think the actions depend on specific hardware robot state. But the subgoal state, that's a generalizable concept that can generalize across different embodiments. Okay, given the GPT output subgoals, we still need to convert it into raw robot actions. So in the bottom level, we'll propose a EMD space single tool planning algorithm with differentiable physics. So specifically, given the current observation and the target given by GPT-4, we predict the next reachable state by taking a small gradient step in the EMD space. The intuition here is that at each time we only deform a little, and differentiable physics can now be readily used since the optimization is now much easier and stabler than a long horizon one. And we then iteratively apply this procedure to finally get to our target. Here we choose the Earth mover distance because it measures the point cloud distribution discrepancy and is a more stable metric than the chamfer distance, because in chamfer you have to compute the nearest neighbor, and that nearest neighbor can change from time to time. So it's not very stable. And another advantage here is that we don't need any demonstration data for this. All we need is just a GPT given subgoal and the differentiable physics simulator. Okay, so we did some experiments on both simulation and real robots. And here's one task. We asked it to make a donut. Here are some visualizations. We can see that our method can learn, or GPT-4 learns how to make a donut by first identifying which tool to use at each stage. And in each substage, we iteratively apply our differentiable physics to solve the small step forward question. And here's another example. We also ask it to make a baguette. And we can see that it performs quite well. The GPT-4 and differentiable physics, when we combine them, it can solve a relatively complex task. Also, we try to kind of align our real robot setup with a simulator and transfer the simulated policy directly into our real world. And we can see that the robot can flatten the doll with a rolling pin. In real-world experiments, we did use a truncated sign distance field to get the point cloud from the multi-view cameras. On the right is the achieved real-world state, and the large language model generated subgoal. And you can see that they roughly align. And yeah, here's the second stage. The robot tries to make a hole in the middle. Okay, cool. So here's an overview of our method, and I would like to thank all the collaborators in this work. The key takeaway here is that although differentiable simulation or optimization is pretty challenging, maybe nowadays we have more foundation model tools to kind of solve it, decompose it into subtasks that can be easily optimizable. Cool. Thanks for listening. Rika and I can both take any questions. Thanks.
Questions?
Thank you both. Maybe I'm being stupid, but I don't actually see what the large language model is adding here in terms of allowing a robot to flatten the dough and make a hole and stuff. Can you just elaborate on how you actually extract useful information from it?
Oh, cool. So the key here is that we find that if you directly optimize, say, from S0 directly to the S2, the gradient is not very good, and you cannot directly optimize using the differentiable simulation. But if you kind of decompose it into subtasks, for example, in the first task, it only needs a small step to kind of flatten the dough. And we also, because we want to also use the differentiable simulators for this subtask, we need to know the target state space, so target state, so we can compute the state loss between S0 and S1. And we are kind of using a hybrid approach. We first use GPT-4V to give the intermediate state. Here is S1 and S2. And in each substage, that means that between S0 and S1, we kind of use differential physics to guide us to go from S0 to S1. We find that this approach is kind of more stable and can achieve relatively complex tasks because GPT-4V can decompose these complex tasks into simpler tasks. Is that clear?
Yep, sounds good. Okay, so thanks. I think we're going to move on to our next speaker just in the interest of time. So our next speaker is Lin Zhao from the National University of Singapore. And Lin is going to be talking about meta learning for robot estimation and control via bi-level optimization.
Right. Thanks for staying until the last. Yeah, I'll keep it short. So basically, our research pretty much aligned with Brandon's research, but more focused on the applications to zone control. Our motivation is that the dynamic optimizations in robot control, like the MPC or MHE, moving horizon estimation, their performance heavily depends on those hyperparameters, right? For example, the weighting matrices and the reference points. And here is a work from University of Zurich. The drone has to seek the varying waypoints based on the current conditions, positions, and velocities while passing through this flying gate. And also the horizon length of MPC and MHE also affects the performance, optimization performance a lot. And those are the key parameters. Typically, people have to manually tune those parameters, but it's quite challenging. It's just like you tune a common filter, right? A lot of times it's not that straightforward, especially the system dimension is large. And those parameters, optimal parameters, may not be static, and they can be time dependent or state dependent as well. So our idea is straightforward. We want to parameterize those parameters, hyperparameters using DN, so that the neural network can give adaptive weightings according to the dynamic environments or different tasks. So basically, we're empower the MPC or MHE to improve the performance or to be able to handle more tasks. And as shown here, you can see that the input to the neural network can be system states, control inputs, or other task-specific signals. And we will give several examples in the zone control and estimation later. So next is how to tune or how to train the neural network, right? So mathematically, you can consider it as a bi-level optimization. So in the low level, it's a dynamic optimization problem you want to solve. And given the hyperparameter theta, you solve either a MHE or a moving model predictive control. In the high level, it's optimization of the DN parameters. and the loss function will be from different a class of different tasks. All right. So in the following, I will give a few applications that we think is interesting. The first is disturbance estimation. So we all know that drones are subject to the various disturbances, such as aerodynamic drag, force, and torque, or downwash, or payload change. Those can significantly degrade the performance of the drone control. And those disturbances are unknown, time varying, and nonlinear. So we propose to use moving horizon estimation to estimate the disturbance. And here is the objective function of the moving horizon. You have the arrival cost, which trying to keep the consecutive estimates consistent. You also have the running costs that penalize the measurement noise and the process noise. This is a model-based optimization, so you also have to subject to the dynamics. And here we simply assume the disturbance dynamics to be a simple random walk model and augmented the original quadrature dynamics with the disturbance model. And last feature is a moving horizon strategy. So this is basically similar to a lot of SLAM algorithm. You move the horizons once you solve it once at a time. And the red letter P, R, and Q, those are the hyperparameters we want to tune, because we know that the performance of the estimation heavily depends on those parameters. And the problem is how to tune them. All right, so we propose this neural MHE, and this is the for the loop in the gray area. Neural network will generate the hyperparameters, and then moving horizon estimator give the estimation, disturbance estimation. Those disturbance, torque, and forces will be used directly in the controller for a feed-forward compensation. In the backward, it's trained by the gradient descent. We're using gradient descent to train the neural network. And you can have the loss function to be as the estimation error if you have the ground truth, or you can have the loss function as the trajectory tracking error, because eventually our estimation is for serving the control purpose. We want to reduce the tracking control error. All right, and of course this is the chain rule. We have 3 parts, and the first and the third parts are explicit function, which is the gradient is explicit gradient, which is easy to calculate. The more challenging one is the middle one. So the middle one, which is in the orange box, this requires us to differentiate through the MHE, which is an implicit gradient, as Brandon has mentioned before. All right, so what is this part? So if naively calculate this gradient using the implicit function theorem, because we know the KD, after we're solving the MHE, we know the KD condition. It defines the implicit function of the optimal solution X and the hyperparameter theta. We can call the implicit function theorem to do this gradient calculation. If the N is the MHE horizon, then compute this inverse will be at least at the order of N squared. And we can do much better because we have the sparsity coming out from the dynamics. So we can bring it down to ON, utilizing the sparsity of the KD condition. Without diving into too much details, eventually we can show that this gradient can be efficiently calculated by a common filter, right, recursively. So that's the major theoretical contribution. We have done some experiment to demonstrate the superiority. We tested the algorithm on the AGL flight dataset, which is from David's group. They also have this neural BNN model, which is our baseline. And this neural BNN model is a hybrid aerodynamic model, consists of 2 parts. The first part is the first principle model based on the blade element momentum theory. The other part is a neural network model, learns the residual force and torques. So we compare our approach with this one. Here is the results. We run over the 13 AGL trajectories, and we train our model over this data set consists of slow speed from 0.2 to 5.2 meter per second, and we are able to generalize to other data sets that contains high speed flights as well. So you can see that both for the force estimation and the torque estimation, we are able to significantly reduce the estimation error. All right, this is the overall comparison between the 2 methods. For the neural MHE, we just simply use a multi-layer perceptron to parameterize the hyperparameters. And we use significantly less neural network parameters, which is 1.9 in comparison to 25K used by neural BM. And in terms of the neural network inputs, we only need to measure the linear and the angular velocities. And for the training data, we use significantly less training data, which is only 10-second long flight data, while the other method has to use 1 hour, almost 1 hour long data. And for the applicability, because our method incorporated the model, so we are able to estimate any external disturbances and model uncertainties, while the neural BM can only estimate the aerodynamic drag force and torques that it has been trained for. But there is a downside. Neural MHE has to solve a nonlinear optimization problem, which has a very high complexity. But neural BM is just evaluate the analytical functions. You can write very fast. Right, we have done some hardware experiments as well. We have 2 sightings. One is a state-dependent elastic cable. There, the force acted on the jaw. The other is subject to the downwash. Right. So we have 3 methods. The first one is neural MHE. The second is the DMHE. DMHE is we use a fixed set of hyperparameter without using the neural network parameterization, but the training method is the same. The last method is L1 adaptive control algorithm. We can see that the DMHE without using neural network oscillates a lot. And neural MHE have a very good tracking performance compared to the other 2 algorithms. The ACE experiment is the downwash experiment. Let me run it. And again, you can see that neural MHE was able to maintain a good height, very accurate height, while suffering the subject to the downwash, while the other 2 methods kind of have a large deviation from the desired height. All right. So far, the performance has been very impressive for the neural MHE. But we do have to tune the seeds, the initialization of the neural network. Sometimes if you have a bad initialization, the training performance can be very bad. So we're wondering whether we can improve that weakness. So we further propose this trust region neural MHE, where we use the second order Hessian information to train the neural network. And interestingly, the Hessian information can also be calculated based on the same common filter, the same structure of the common filter. So you have the 2 back propagation loop. One common filter solves the MHE gradient, the other solves the MHE Hessian. The result is very impressive. So here you can see that the gradient descent, the GD represent the previous first order methods, and the performance oscillates or varies a lot. Given different seeds, you may have a very quick training or very slow training. But for the trust region method, the performance improves very quickly and very robust against the neural network initialization and also the learning rates as well. And we were able to train the neural network within less than 5 minutes, and also get better training loss, better performance as well. All right, so this is a comparison over the 3 different algorithms we have mentioned. And you can see that the last row of a trust region neural MHE, we're able to reduce neural network parameters to even about 300 parameters. And the data we need is only 0.25 second long flight data. This is collected at 400 Hertz. So we only use 100 data point to train the small neural network, and we're able to achieve a better performance, estimation performance. So a good physical model plus efficient training algorithm can give us a very good estimation performance. All right. Another application we're interested in is learning the age of flights. So here we're trying to control a quarter flying through a rotating and translating gate. So it requires us to give the right control at the right place and at the right time. The idea is similar as before. We use the same idea. We use DNN to parameterize the tracking references and weights according to different gate weights, orientation, and their velocities. So that's a general idea. So here is a general formulation. The neural network output will be the pose, the positions, the orientations, and the predicted time at which the quarter flies through the gates. So those are the output of the neural network. And those parameters, the Z vector, will be used to generate the references and the weights that are being used by MPC. And the optimal solution from the MPC will be evaluated. And those basically consist of the clear avoidance cost and also the control cost and some other costs. And then we just do a gradient descent and train the neural network. All right, so here are just some successful attempts. We trained this neural network in our very simplified model, and we tested in high fidelity simulators, the gene parabolic zones, which consider additional motor dynamics, drags, and ground effects. Lastly, we move from a single correlator to multiple correlators. We consider the cooperative transport problem. Typically, these problems are solved, the motion planning and control are solved by distributed MPC, given that the correlator are sparse coupled, because the only coupling is between the zone and the load, not between the zones. So this is the sparse coupling. But however, tuning the MPC weights in this case is very challenging. Here are some peculiarities. For example, the weights are different for different agents in cases where the task is asymmetric. For example, if you want to control your multi-lift system, this cooperative transport system, to go through a narrow window, then you need different weights for different drones. And also when the load weight is not evenly distributed. Actually, we're interested in when the geometric center of the load is different from the center of mass. So in this case, you also need different weights for different agents, correlators. And also, if you give it a try, 3-agent multi-lift system and 4-agent multi-lift system are also different. You also need to tune different weights for them as well. And this is so basically different weights for different number of drones you use. We want to get rid of these tedious tunings, and we want to develop an algorithm to automatically tune those weights. All right, another challenge is the same to real gap. Here basically is the string dynamics. It's a hybrid because you have the slack and taut two states. And once it's taut, you also have the stiffness, which is difficult to simulate in the simulator, which easily cause numerical problems as well. So in MPC, people typically consider a very simplified model, and they only constrain the string length. Because if you have a hybrid model in the MPC, then you couldn't meet the real-time efficiency. It will cause a lot of time to compute the MPC. However, in high fidelity simulation, people typically use a spring damper model. When the string is taut, you have the string damper model. Otherwise, the tension of the string is 0. So the string damper model is used in our simulator. We haven't done any hardware experiment yet, but even from the MPC model to the high fidelity simulation model, we could find some issues with the training. So basically, with this cable suspended multi-lift system, the cable dynamics, the string dynamics makes it very sensitive to the model errors. And the question is, how can we bridge the gap? So we combine and extend the several existing method and proposed this auto multi-lift framework. This is a distributed closed loop learning framework. Before, we only propagate starting from the optimal solutions outputted by the MPC. But now, in order to bridge the gap between the MPC model and the simulator model, we propagate starting from the actual simulated states from your simulator. So here, the loss, again, can be your trajectory tracking error. And first, we need to differentiate it through the real dynamics using the real measured states from the system, from the high fidelity simulator. And then, just as before, we differentiate through the MPC and then differentiate through the DNN. And then we tune the neural network of each of the correlator and the load as well. All right, we have done 2 simulations. One is to learn adaptive weightings. We want to control the correlators to the multi-lift system to track a circular trajectory. And for the load, we consider the unevenly distributed load. So the geometric center is different from the center of mass. And we want to control the geometric center to track the circular trajectory and also keep the desired pose as well. So here we're tuning the MPC parameters Q and R. And the first simulation is to using the open loop learning. Basically, we back propagate starting from the MPC output. And you can see that over a few rounds of a few episodes of training, you apply them to the real system or that more high fidelity simulator, it will lose stability. It causes instability. But if you consider the closed loop learning, you can actually successfully control the curators, the group of curators to move the load successfully, and pay attention to the pose of the rigid body load as well. And after enough rounds of training, the pose of the load will also be controlled very successfully in a flight pose. Right. Our last simulation is about the adaptive reference. So here we want to control the multi-livery system to pass through the two slots. And during this process, the curators has to spread to lift the load. And here we are learning the tension references here. Because the tension references you give to the MPC is based on some static conditions or stationary condition, which is not enough or inaccurate. Okay, I will just quick show the simulation here. So at the bottom, the plot shows the tension force from the 6 curators. And in the first simulation, the curator won't be able to pull the load pass through the slots. And after training on the right, you can see that we're able to pull the load and pass through the slots. And the tension force also shows more dynamic and large variations. All right, I think that's all. I want to thank my students and my funding sponsors, and these are the paper list. Yeah, thanks everyone.
Thanks. Okay.
Thanks. That was very interesting here. The neural networks are not, I mean, to call them deep is probably an overstatement, right? Because they're small and they have not a lot of weights. So are we at a point where we want to, think about what's in them and whether we need neural networks at all, right?
Thanks. We call it deep because we have 2 hidden layer. But we have, we should have tried maybe 1 hidden layer and trying to see whether deep is really needed or not. But we do have an ablation study. We remove the deep neural network and only consider a fixed set of parameters. And actually that is in my video. And here you can see the difference. So in the middle is without the neural network, only a fixed set of parameters. So you can see the curator is really very jumping here. But on the left is with the neural network, right? I think that actually shows you the importance of neural network. It gives you more dynamic parameters.
Okay, so I think we're all getting pretty sleepy and maybe in need of food. So I'm going to pass it off to Frederike for some closing remarks. Oh, sorry. And let's thank our speaker when we're signed. Sorry.
All right, I will keep it super short, trust me. There are not even slides for this part. I just want to take a quick moment to thank some people. So first of all, I want to thank all the amazing speakers who gave a really nice overview of very cool progress in optimization. Then I want to thank all my co-organizers who were behind this. So you saw our hosts, or the chairs. So Connor, Justin, Ajay, I don't know if everyone is still here. And then there was Alberto always doing a lot of stuff in the background related to Zoom and setting things up. And then Tim helping with the posters and Hank. So yeah, this was all a joint effort. Also, everyone has helped with putting this program together. So just a quick thank you. And then also I want to thank Chris and Katsu, who were the workshop chairs, who did a great job at organizing all the logistics. And then finally, thank the audience for being a fantastic audience and many interesting questions. And also thank you for handling the poster situation well, which was a bit crowded maybe at some points, but I hope that you all got a lot from this. And just a last point, we're doing this workshop for the first time, but I think there was a lot of positive feedback, and we would be really interested to keep going with these kind of workshops in the future. So if you liked it and if you have some ideas of what to include at next editions of this, and maybe you think that one frontier was missing from our list of frontiers, or feel free to come to talk to us. We're all going to be here at RSS during the whole week. So yeah, feel free to reach out. You can also be co-organizers maybe in future years. And yeah, with that, enjoy the rest of the conference, and thank you again for coming.